Okay, so these are just some extra questions from Unit 1718, where we're still looking at derivatives of exponential and logarithmic functions. So we've got 3 questions here that we're going to go through. The first one here, find the slope of the tangent to the curve, and we've got this function written out here. Make sure you've added the exponent 3 here onto the argument of the log function, and we want to find this at x equals 5. First thing to remember about these kinds of questions is, well, you want to take the derivative if you're finding the slope of the tangent, but you have to take the derivative first before you sub in your value of x. I know I've said this a million times, but just you got to do the derivative before you can do anything else. Now this is a bit of a complicated function here. It involves both an exponential function and a logarithmic function. So I think the best strategy to pursue here is to actually split it up, and we'll do the derivatives individually, and then we'll put them back together. Because what we can see here is we've got our exponential function, 10 to the 2x minus 9, multiplied by our logarithmic function. So we're going to have to use the product rule. So we'll call this our function u. We'll call this our function v, and then we will figure out what our derivatives are. So if u is 10 to the 2x minus 9, how do we find the derivative of that function? What's the rule for exponential derivatives here? What do we know? Yeah, we're going to have a ln term in there. Right, so we've got our original function, which we multiply by this ln, and we have to have this ln thing in here anytime we're working with a base that is not e. So our base here is 10, so we have to have the ln of 10, okay? And then, because this is our u is a composite function here, we want the derivative of that function that's up in our exponent here. So derivative of 2x minus 9 is just 2. So that would be our derivative u primed. Now v is log to the base 10 x squared minus 3x, and that whole thing is cubed. Okay. We've got a log function, and then inside the log function we've got something cubed, and then inside that thing cubed we've got x squared minus 3x. So we could use chain rule twice here, or we could use a little trick involving the laws of logarithms. How could I simplify this using logarithm laws? What can I do with that exponent that I've thrown up there? Yeah, I can put it out front. And that basically takes care of one of those functions that we were going to need to use our chain rule for. So if I just turn that into a constant out in front, when I do the derivative of the log function, I know that the derivative of e prime is just going to be 3 times the derivative of that log function. That's our old constant function multiplied by a constant rule. So I'm going to have a 3 times. Now how do I do the logarithm, the derivative of a log function, if I don't have this base here? Okay. I've got to have the change of base rule, what's going to produce that term of ln of the base. So I'm going to have a ln 10 popping up again. And remember, the derivative of ln is 1 over x. So the derivative of log is 1 over, instead of x, we've got x squared minus 3x. Okay. We need our ln 10 down here in our denominator. And this whole thing gets multiplied by the derivative of what is inside that log function. So the derivative of x squared minus 3x. So let's multiply this by 2x minus 3. Okay, and there is v primed. So now we can put these things together using the chain rule. We are going to have, let's see, where are we here? Y primed is going to be u primed, which is 10 times 2x minus 9 times ln 10 times 2 times our original function here for v, and I'm just going to do this as 3 log base 10 x squared minus 3x. Okay, so that is u primed times v. To this we have to add u times v primed, which was 2x minus 3, all divided by x squared minus 3x, all times ln 10. So once again, this is u, and this is v primed. Okay, so this is our big long expression for a derivative. And we want to evaluate this at x equals 5. So this should simplify a fair bit here. So if we just do this term by term, x equals 5. So if we put it into this first term here, we get 2 times 5 is 10, minus 9 is 1. So 10 to the 1 is just 10. We'll keep the ln 10 there. 2 times 3 gives us a 6 there. And then, let's see, if we sub it into this log, we get 5 squared is 25, minus 15 is 10. So log to the base 10 of 10, plus, we get another 10 to the 1. And then, what do we have over here? 2 times 5 is 10, minus 3 is 7, so we have 21 up top, and then 10 log 10 down in the bottom, 10 ln 10 down in the bottom. Okay. So how can we simplify this a bit more? Over here, the 10 and the 10 cancel. What about log to the base 10 of 10? Because it's just 1. Okay. And so we're left with 60 ln 10 plus 21 over ln 10. Okay. And if we wanted a decimal answer, we could evaluate that. If we wanted the exact answer, we would just leave it like that. Nick?
Can you put the ln 10 to the top to make the factor negative 1 and then factor out ln to the negative 1?
If you really wanted to. That doesn't help you. The reason you usually do that is if you had a variable there and you wanted to factor it to solve for the variable, but we've substituted in, so that would just, at that point, it's just pushing numbers around. Okay. Brody.
So you would have to sub to 5 and back to the original equation because we're supposed to find the slope of this given? Or is it just because we're playing slope of the tangent, we're just doing that? So they would
Yeah.
actually put the equation of the tangent?
Yeah, you would have to go through, you would evaluate the slope, you would go back, you'd get your x and your y values from the original. But because they just ask us for the slope, we can stop there at that. Okay? All right, let's take a look at the next one here. Curve x squared times ln x has an absolute minimum that occurs once over its domain. Find the minimum value. Okay. How should we start this one? What do we want to do first? Yeah, it's a good idea. We don't really need the range, we just need the domain. So our domain is going to be x is an element of a real such that the domain of we've got 2 parts here. We've got the x squared and we've got the ln x. For x squared, we can have any real number. There's no restrictions on that. What is the restriction that is always placed on logarithmic functions? Yeah. So we'll just say that x has got to be greater than 0. Okay. Now, if we're looking for a minimum, we are looking for, well, we've got to find our critical numbers. So we are going to take our derivative and set it equal to 0 here. So let's find our derivative. We've got x squared times ln x. So we know that we're going to have to use product rule. So derivative of the first part, 2x ln x plus x squared, and what is the derivative of ln x? 1 over x. Okay. So this simplifies then to 2x ln x plus, oops, not an equal sign, but a plus sign, plus x. X squared divided by x is just x. And if we're looking for critical numbers, you probably want to factor this. So factor out the x, 2 ln x plus 1. Okay? And as we've said, we're going to want to find our critical numbers. Okay. So the critical numbers that we're interested in are the ones where y primed equals 0, because those are the ones that we can use that will give us our local maximum or our local minimum. Okay? We could also find where y primed does not exist, okay? But those critical numbers usually only give us vertical asymptotes or something weird. So they don't correspond to local maximum and minimum. So we don't really care about these guys in this kind of question. So if we're setting this thing equal to 0, what do we got? 0 is x times 2 ln x plus 1. Well, we've got two things that we want to solve here. X equals 0 or 2 ln x plus 1 equals 0. This one right here, x equals 0, that was the easy one to solve. What's wrong with this one, though? Not in the domain, so we can just cross it out. So we're left solving this one here. So 2 ln x is -1. Ln x is -1/2. And how do we solve it from here? We know that ln x is equal to 1/2. How do we solve for x? Magic. There's like some spell that you can learn and this. No, come on. Yeah, you're right. You want to use the power e thing. So we're going to use e as our base, and we'll do e ln x, e to the -1/2. Okay, so we raise both sides of this to the base e. And what do we know about e ln x? Yeah, the e and the ln sort of cancel each other out, and we're left with x equals e to the -1/2. Okay. So there's our x value of our only critical number. And ordinarily what you would do is you would say, okay, this is my critical number. I know this is a local maximum or local minimum. I'm going to apply my second derivative test to figure out whether I have a local minimum or local maximum. In this case, because of the way I've worded the question, you don't have to. Because I'm telling you that there is an absolute minimum that it only occurs once. So if there's only one critical number, that has to represent an absolute minimum. Okay, so we can dispense with second derivative test in this case, and we'll just find that minimum value. So we'll take our x value, sub it back into our original function here, and see what we get. So e to the -1/2 squared times ln of e to the -1/2. So what do we get here? Well, let's see. E to the -1/2 squared is just going to be e to the -1 times, I can bring down that 1/2. I get 1/2 ln e, but ln of e is just 1. So I end up with -1 over 2e. And that's my maximum, or my minimum value. Okay. Okay. All right, last question. The number of bacteria in a culture at time t is given by this function here. How is the number of bacteria changing at t equals 20 hours? What's the large, and part B, what's the largest number of bacteria in the culture in the first 50 hours? So for part A, if we're interested in how the number is changing, what do we want to find about this function? Yeah, the slope of the tangent, or we want to find the derivative. Okay, so let's take our function, and I mean this one's written a bit weird here. Let's expand this first. 30 times 1,000 gives us 30,000 plus 1,000 e to the minus t over 30. Okay. I think that'll make it a little bit easier to see how we're going to do our derivative, because we've got the derivative of this plus the derivative of this, but this is just a constant, so it goes away. And so we're going to have 1,000 times the derivative of e to the negative t to the 1 over 30. And we want to think about that as e to the negative 1 over 30 times t. So we're taking the derivative of an exponential function, base e, so we're going to have our original function times the derivative of that expression that's up in the exponent. So the derivative of negative 1 over 30t is just negative 1 over 30. So we multiply this out and we get negative, say 1,000 divided by 30 gives us 33.3, and so on, e to the minus t over 30. And there's our derivative. So for part A, if we're interested in what happens at t equals 20 hours, let's sub this in. T equals 20, n primed is going to be this expression that I just wrote, evaluated at negative 20. And we punch this into our calculator, and we get negative 17.1. So how is the number of bacteria changing at 20 hours? What's it doing? Yeah. It's decreasing at a rate of 17.1 bacteria per hour. Part B. We want to find the largest number of bacteria in the culture in the first 50 hours. So let's start off with our domain here, which is, if we're looking at the first 50 hours, we're interested in t values between 0 and 50. Okay. And if we're interested in finding where the maximum occurs, well, we've got to find our critical numbers. So let's take our derivative. Let's just write out critical numbers. We want where n primed equals 0. So we know what n primed is. It is negative 33.3 repeated e to the minus t over 30. Okay? And we want to solve that for t. How do we solve this for t? Okay, well, we could deal with the negative 33.3 first by dividing through both sides. And then take the ln of both sides. What's the problem with what I've written here? I can't take the ln of 0. So this is telling me that there's actually no solution here. So now what do we do? Well, we still have to find our maximum here, okay? So normally in these questions, right, we take the derivative, set it equal to 0, find our critical numbers, because our critical numbers tell us where we can have local maxima and local minima. This is telling us that we don't have a local max or a local min. Yeah, so we've got to look for absolutes. So we got to check our two endpoints here. So let's check our endpoints. T equals 0, t equals 50, and we would just plug those numbers in and see what we get. So we would get 31,000, and we would get 30,189. Okay. So what is the question asking us? Well, it was asking us what is the largest number of bacteria in the culture in the first 50 hours. The largest number, we can just see from comparing these two numbers, wait, is this past tense or present tense? What is the largest number? The largest number is 31,000 bacteria. Okay. Now, where did that maximum occur? It occurred at t equals 0, which is the start of our domain. Why does it make sense that it occurred right at the beginning?
It's a declining rate.
Yeah. We had a declining, the slope of our tangent was negative, so our function was decreasing at 20 hours. When we looked for our critical numbers, we didn't find any critical numbers, so we know we have no turning points. So if our function is decreasing at one point on this domain, and it has no turning points, it's got to be decreasing everywhere. So if it's decreasing everywhere, the maximum has to occur at the very beginning, which is exactly what we found. All right, and I think that's all we're going to do.